This video continues the presentation for This video covers section 13.4 in our textbook. The equilibrium constant expression sets up a relationship between the equilibrium concentrations and the equilibrium constant at a given temperature. For example, let's look at a reaction of 2A plus B goes to C, and write the equilibrium constant expression for this reaction. The equilibrium constant Kc is equal to the equilibrium concentrations of the product C raised to the fourth power divided by the concentration of the reactant A squared and the concentration of reactant B. This particular equation has four variables, so we would need additional information in order to evaluate it. Where do we find additional relationships or information? Stoichiometry provides another relationship between the concentrations of reactants and products. And in a similar way, like we use stoichiometry tables during our review sessions, ICE tables are a convenient way to summarize these relationships and solve equilibrium problems, either for the value of K or the value of the equilibrium concentrations. ICE stands for initial. ICE tables are set up using concentrations or partial pressures depending on whether you have or want to get a Kc or a Kp. ICE tables can be used to calculate the equilibrium concentrations of species if the equilibrium constant K and a set of initial conditions are known. Let's look at how we would fill in an ICE table for our sample reaction of 2A plus B goes to C. Since we are using an expression for Kc, we want to complete the table using concentration values. We can still use the mole relationships from the balanced chemical equation because changes in molarity are proportional to changes in moles, as long as the volume stays constant. The initial concentrations are usually given in the problem, but if not, you can use variables to represent them. Here we're using a subscript 0 to indicate an initial concentration. Again, if these values were given as numbers in the problem, you can go ahead and put the numbers in. The amount of change is sometimes given in the problem, but we usually use x values. Since A has a coefficient of 2 in the balanced chemical equation, we typically represent the change in the concentration of A as minus 2x. The minus sign is used here to show the loss of reactant A. This assumes that the reaction will proceed in the forward direction. If the concentration of A is decreased by 2x, then the concentration of B must only decrease by x, since its coefficient is 1 in the balanced chemical equation. Similarly, the concentration of C must increase by 4x because the balanced chemical equation tells us that for every 2A that react, 4C will be produced. The equilibrium row is usually written as the sum of the initial and change rows for each chemical species. So for A, we have the initial concentration of A minus 2x. For B, we have the initial concentration of B minus x. And for C, we have the initial concentration of C plus 4x. Since the equilibrium constant expression contains the equilibrium concentrations of the reactants and products, we use this last row to set up our K expression. Solving these types of expressions then depends on the additional information given in the problem. If the K value is known and the initial concentrations are all known, then the only unknown in the problem is x, and the equation is solved for x. Ice tables can also be used or set up using partial pressures. For example, if we choose to write our K expression in terms of partial pressures, we would want to use partial pressures in our ice table, but otherwise everything else is similar. Notice that we're starting with an initial partial pressure of A, an initial partial pressure of B, an initial partial pressure of C. Our change row is the same with minus 2x, minus x, and plus 4x. And then the equilibrium row, again, is the sum of the initial and change rows. So again, when we set up our Kp expression, we would be plugging in the equilibrium partial pressures of the reactants and products into our Kp expression. Again, solving these types of expressions depends on the additional information given in the problem. If the Kp value is known, and the initial partial pressures are all known, then the only unknown is x, and the equation is solved for x. On the other hand, if one of the equilibrium partial pressures is known, then that expression can be used to solve for the value of x. The remaining videos in this chapter give several examples of how to solve these types of equilibrium problems.